Yeah. So let us now look at the concept of negative feedback. Okay, so we'll try and understand negative feedback at a very intuitive level. First, let us try to understand negative feedback at a very intuitive level. Let me see how much of it I'll be able to explain you. Okay, suppose you are going on a bike. Okay, suppose you are going on a bike and you are very much a law abiding citizen, and you know that on most of the roads in our city Hyderabad, okay, the speed limit is 50 kilometers per hour. Okay, so you shouldn't be crossing this limit. If you cross, okay, you will be fined, and you know the procedure. Okay, so you are a law abiding citizen and you don't want to cross this limit. Okay, right. So what is happening now that you are driving the bike? Okay, so let us see what is happening. Okay, so the desired speed, okay, so the desired speed is what? Is nothing but 50 kilometers per hour. Okay, 50 kilometers per hour. Suppose, okay, uh, you are going at say you just started the bike, you are just in the first gear or second gear, and suppose you are only at 10 kilometers per hour. Okay, so how do you read the speed? How do you get the actual speed of the bike? Okay, so the actual speed of the bike you can get it from, I think you all know there is a speedometer on all bikes. Okay, where you can actually read the speed. Okay, so suppose this is where you read the actual speed. Okay, so suppose the actual speed is only 10 kilometers per hour. Okay, so what do you do? Okay, you immediately try and accelerate. Okay, right. So what happens here is okay, so this actual speed, you read the actual speed, that is the current speed of your bike. Okay, and then what you do is you kind of compare these two. Okay, you kind of compare the desired speed, that is 50 kilometers per hour, with the actual speed. Okay, and then take the necessary action. You know that there is a 40 kilometers per hour margin here. Okay, so you know you, and then you try and accelerate. Okay, suppose now your actual speed is, say, suppose 30 kilometers per hour. Okay, what do you do? Again, you read the speedometer, and then you know that the actual speed is 30 kilometers per hour, but the desired speed is 50 kilometers per hour. There is still margin. Okay, and then you accelerate. But what is the difference when you accelerate in these two cases? Okay, so when the actual speed is 10 kilometers per hour, okay, so you accelerate a bit. What do you say? You give more acceleration. Okay, so when compared to the case when you are at 30 kilometers per hour, it will be a bit gentle acceleration. I hope you are able to understand these two cases. Okay, suppose your actual speed is now 49 kilometers per hour. Okay, you are almost there. What do you do? Okay, your acceleration will be even more gentler. Okay, even more gentler acceleration. Okay, so because you are very near to the, very near to the desired speed. Okay, so what is happening here is intuitively what you do is, okay, you take the difference between the desired speed and the actual speed. Okay, so what is happening here is the difference is happening between desired speed and the actual speed, and you get something sort of error. Okay, and then depending on this error, how far is your actual speed from the desired speed, and then you take the action accordingly. Okay, and then you take some action over here. Okay, depending on the error, that is, you give the acceleration gently or you give the acceleration in a very, okay, so you really give the acceleration in this case when the actual speed is 10 kilometers per hour. Okay, you really accelerate it like anything compared to your 49 kilometers per hour case. Okay, so based on the error of your desired speed and the actual speed, you seem to be taking some action. Okay, Now let us try to understand what this action is intuitively. Again, I am not including any high-end mathematics over here. Okay, so this is where you are sensing the speed, okay, through the speedometer, okay, through the speedometer. Okay, so this is a desired speed 50 kilometers per hour. This is already you have it in your mind because of the rule of the city. Okay, so this is the sensing speed from the speedometer, and we take the difference of these two and we get the error. Okay, and depending on that error we take an action. Okay, if the error is too much, okay, so that is when you are going at 10 kilometers per hour, the error is 40 kilometers per hour, you take action. Okay, you accelerate wildly, whereas when your actual speed is 48 or 49 kilometers per hour, your action will be much lesser. That is, your action will be much gentler, your acceleration will be much gentler. Okay, right, now let us try to get a intuitive understanding of what this action would be. Okay, right, so again, in order to cut down maths, I want to introduce negative feedback only, uh, or rather I want to give just an intuitive understanding. I don't want to give complex math over here. Okay, so I might be sometimes oversimplifying things, but that is what is required to get a intuitive understanding right now. Okay, so you are doing the same scenario. Now you are going on Hyderabad roads, so the desired speed is say 50 kilometers per hour. Okay, right, and then you know that you are sensing the speed from a speedometer. Okay, you are sensing the speed from a speedometer, and let us say the speedometer is stuck. Okay, it happens more often than not, isn't it? Okay, suppose this speedometer is stuck at say 30 kilometers per hour, it is not going above, not going below. Okay, suppose this is your speedometer 0, 10, 20, 30. Okay, this speedometer is stuck at this 30, it is not going above or below. Okay, now what do you do in this case? Okay, so okay, the error is always constant. Okay, the desired speed is 50 and the speedometer is showing 30 kilometers per hour. So what is the nature of the error here? The error is constant always because the speedometer is stuck. Remember, the speedometer is stuck at the 30 kilometer per hour mark, and your error is almost always constant. Okay, but your action, would it be constant? Would your action be constant? What do you do? Okay, because your error is like 20 kilometers per hour margin is there. Okay, you try to accelerate. Okay, you try to accelerate. Okay, suppose this is time, and this is say this is your action. Okay, you try to increase the speed, increase the speed even more. You try to put on more speed. Okay, to in order to reach in order to reach your desired speed. Okay, but you didn't know that the speedometer got stuck, but it would ideally take some time, maybe some 30 seconds before you realize that something is wrong. Okay, but I'm speaking about the time before which your intuition kicks in and tells you that the speedometer is stuck. Okay, so I'm speaking about that time. Okay, so before you realize, what do you do? Okay, because it is showing a constant error. Okay, it is always at 30 kilometers per hour. You increase the acceleration. Okay, so you increase the acceleration. Okay, right, now suppose your speedometer is stuck at 48 kilometers per hour. Okay, what do you do now? The error now in this case is also, what is the error? The error is now also constant at 2 kilometers per hour. But what will your action be? You know that you're almost there at your desired speed. Okay, so if this is the error at 20 kilometers per hour, okay, so you wouldn't accelerate so much. I think we have seen it in the previous discussion as well. Okay, you would be accelerating much gently. Okay, when your error is 2 kilometers per hour, you'd be accelerating much gently when compared to your action when your acceleration when the difference is 20 kilometers per hour. Okay, right, now so why I'm doing this is I want to understand the nature of this action block. I told I'll be taking the difference between the desired speed and the actual speed here, okay, from the speedometer, and then I said I'll be taking some action. Okay, now I want to know what this action looks like. Okay, so that is what we are trying to do. Okay, so that is why this example where the speedometer is stuck. Okay, now so let me try to understand this action block. Okay, so when the error is constant, okay, so in these two cases the error is constant, isn't it? Once the error is stuck at 20 kilometers per hour, and second case the error is stuck at 2 kilometers per hour. So when the error is constant, what is this action block doing? Okay, so the action block is doing something like this. Okay, so if it is 20 kilometers per hour, okay, if the constant error, it is doing something, okay, of this manner. Okay, you will be accelerating. Okay, let me take another color. Okay, if your error is 2 kilometers per hour, okay, and you know that your action block is doing something like this. Okay, so you are still accelerating but at a much more gentler pace. Okay, so the slopes of these two lines are different. Okay, so which block actually does this? Okay, you are giving a constant input, okay, and you are um, you are getting a function in time. Now this is a constant input to the action block, but what is the output? The output is a function in time. Now seriously, this is because this is a function in time, and this is a first order function in time. This is somehow related to t, like some kt, isn't it? Okay, where k is the slope. So this one might be k1t and this one might be k2t, okay, and so on. So what is the mathematical operation that does this? You are giving a constant function and you are getting a function that is linearly dependent on t, isn't it? Okay, so from whatever I know, that is what an integration does. Okay, so that is what an integration does. Suppose you have 2. What is integral 2 dt? Integral 2 dt is nothing but 2t. Okay, so the same thing is happening here. Okay, so your error is constant 2 kilometers per hour. Okay, but what is your action block doing? Okay, you are supposed to increase your acceleration gently. Okay, so that is nothing but, okay, you increase the acceleration with 2t. Okay, so suppose your difference is 20. Okay, 20 integral dt is nothing but 20t. The slope is much higher here in this case. Okay, so the action block is nothing but your integration block. This is at a much intuitive level. Okay, so let us see now the feedback system. Okay, so what is happening in the feedback system? You have a desired value. Okay, you have a desired value. Okay, what do? You take the difference of the desired value from the actual value. Okay, the actual value. Okay, and then this difference you call it the error, and on the error, what do you do to the error? You integrate it over time. Okay, that is integral dt, and then you get the uh, output over here. Okay, so this is nothing but a negative feedback system. Okay, now why did we try to understand negative feedback system? Because we wanted to design an amplifier in which the output is k times vi. Okay, in our IC741, that is the open loop amplifier. Okay, we see that if the output is responding to vp and vn, okay, the output is responding to vp and vn, but what is happening if vp is greater than vn? Okay, my v out is equal to plus vcc. Similarly, if vp is less than vn, my v out is equal to minus vcc. I am not able to control things. Suppose I want v naught to be exactly twice vi. Okay, so I am not able to design such amplifiers wherein the gain setting is in my hand. Okay, wherein I am able to control this gain, this k is called gain. Okay, wherein I am able to control this gain. Okay, so that setting is not in my hand when I use the IC741 in open loop. Okay, when it is in open loop, I am not able to control things. Okay, so that is where we have studied the concept of negative feedback. Now let us try to design an amplifier where V0 is equal to kV1. Okay, right. Okay, so suppose this is my input Vi. Okay, so like we discussed in the negative feedback system. Okay, so this is my V0. Okay, and this is supposed to be kVi. Okay, so I do some sensing operation here. And this is Vi, that is the input, and I take the difference over here, and the error, that is the input value, that is this mm, uh, desired value is in this case desired value will be v0 is equal to kvi, and I compare it with uh, vi. Okay, and then the same thing. Okay, so this is my integrator. Okay, right, but there is a small catch over here in this type of behavior. Okay, I am trying to design v0 to be k times vi. Okay, and I don't know if I reached it. Okay, are you able to sense the paradox? Okay, I am trying to design v0 to be equal to kvi. Okay, but what I rather do not know is if I reached v0 is equal to kvi, because I don't know if I could reach v0 is equal to kvi. Did it ever happen? Can I sense it? I don't know, because I'm still designing it. Okay, so there is a small paradox over here, but what I can rather do is I can check if vi is equal to v0 by k. I can do this. Okay, isn't it? I can actually do this. Okay, because amplification, okay, v0 is equal to kvi may be difficult to me, but uh, what is happening here, v0 is a fraction of itself, that is v0 by k, that is obtaining a voltage that is fraction of another voltage. Okay, okay, this I can do. Okay, so this is nothing but a potential divider, isn't it? So this is nothing but a potential divider. So let us take the example of a potential divider. Okay, so you have some vd over here. Okay, and suppose you have, okay, so this is r1 and this is r2. We know this is a potential divider. Okay, so what will be the voltage drop across r2? Suppose this is my ground. Okay, suppose I want to find va. Okay, so what is va equal to, okay, we know that if this current is equal to I, okay, so applying kvl over here, we know that vd is equal to I r1 plus I r2. Okay, and we know that from this I is equal to vd by r1 plus r2. Okay, but what is va? va is nothing but drop across r2, and drop across r2 is nothing but ir2, and from this equation what is I? vd by r1 plus r2 into r2. Okay, so this is the potential divider network we know. Okay, so r2 by r1 plus r2 I can represent as vd by k, isn't it? So if you have a simple potential divider network, okay, and some voltage source here, that is vdd. Okay, so va will be some fraction of vdd. Okay, so the same thing is happening over here. Here I am set out to design v0 is equal to kvi, but I wouldn't know if I have reached kvi. So what do? I would rather compare these two elements. I would rather compare vi with v0 by k, because I know amplification is difficult, but I know that this type of bringing down the value is easy and can be easily achieved with the help of a potential divider. So what I am doing now is, in constructing this amplifier, suppose this is my input Vi, okay, so I am having this difference, okay, and then you know that this is an integrator, okay, this sigma is for difference, okay, over here. So this is summing, okay, so this is plus minus, so this gives me Vi minus this value, okay, so and this is V naught, okay, and I am putting a potential divider over here, okay, and I am choosing these values such that this resistor is k minus 1 R and this resistor is R. If you see that, you will realize that this potential, okay, will be equal to V naught by K, okay. You plug in the values of k minus 1 R in this R1 and R2 respectively, okay, and then see what will be the value of Va, okay. This is simple Ohm's law, okay. Right now we are applying this V naught by K as an input to this thing, okay. Now when does this stop? Okay, so this is your driving analogy again, okay. So the error, okay, so the error will be 0, okay, the error will be 0. When does that happen? When the desired value is equal to the actual value, when the desired input is equal to the actual input. In this case, when Vi is equal to V naught by K, V naught by K may be desired here, and V naught by K is the actual value and Vi is the desired, okay. Only then this error is 0 and this output V naught will be equal to K times Vi, okay. So this type of integration continues, okay, till your error becomes 0, okay. So you think of that speedometer analogy, okay, so that should make sense. Now what your op amp does is, okay, so it combines all these properties inside itself, the triangle that I draw, okay. So what is happening? Okay, so the plus and minus, see what is happening in your system here. You have a positive terminal and you have negative terminal, and some difference is happening over here, okay. So the same thing, okay, so your op amp has a positive terminal and a negative terminal, okay. So what is there inside this triangle is this beautiful mechanism, okay. So it can take the error, this triangle, and it can integrate it, that goes into the, okay, so that goes into this triangle, okay. So this portion of taking the difference and integrating it over time is taken care of by the triangle, okay. So that is what is happening inside that op amp. But what is the outer thing that we have? So we have some k minus 1 into R here, and this is nothing but R, okay. This is nothing but my Vi, okay. So this is where I am applying my, okay, so this is where I am applying my V naught by K. I know that this will be equal to V naught by K, okay, right. So this is called a closed loop amplifier, okay. We are not using the amplifier in open loop anymore, okay. So the loop is closed as in there is some sort of connection between output and input, okay. So this is your basic negative feedback system, okay. It is also called as a closed loop amplifier, okay. So what is happening, okay, here, okay. So this is basically a negative feedback system, okay. And what is happening, what do we do in the negative feedback system? Okay, we equate the desired value with actual value, okay. So that is what happens in a negative feedback, in a actual value. So that is what happens in a negative feedback system. So here what is happening? So here Vi is made equal to V naught by K. Okay, so the desired value and actual value are made equal here. This is due to what? This is because of negative feedback. We have seen that bike example wherein we use the negative feedback always to correct the error. Okay, so that error taking part and the integration part. Okay, so that is taking the difference between these two and then integrating it over time is achieved by this op amp internally. Okay, you don't need to worry about that function taking the error and integrating it. So that is done within the op amp. Now we are learning things at black box level. Okay, so you need not worry, you can trust your op amp that it is doing that. Okay, it is doing just that. In fact, it takes the error and it integrates it. And what is happening here because of the negative feedback? What is happening here? The positive terminal Vp is being equal to the negative terminal Vn, isn't it? Okay, because of the negative feedback, what is happening? Vi is equal to V naught by K. So that is when we say V naught is equal to kVi. Okay, so when does this happen? When does V naught become kVi? V naught becomes kVi when it is in negative feedback. And what is happening because of the virtue of negative feedback? See, I use the word virtue because it is doing you good things. Okay, so what is that virtue of negative feedback? Because of the virtue of negative feedback, what is happening? Vp is becoming equal to Vn. Okay, so the thing that you saw over here, how do you proceed in electrical terms? Okay, how do you proceed in electrical terms is nothing but like this. Okay, so this is Vi and this is V naught and this is in negative feedback. Okay, so how do you identify? One simple test with which you can identify if it is in negative feedback or not is, see, a portion of output is being fed back to the negative terminal. Okay, a portion of output is being fed back to negative terminal. So it is a negative feedback system. When it is in negative feedback, what is the virtue of negative feedback? Your Vp becomes equal to Vn. Okay, so what is Vp here? Vp is equal to Vi. And what is Vn here? Vn depends upon the ratio of this. Okay, so this is nothing but my Vn. Okay, I can see I can still use my potential division over here. Some of you might have doubt like there might be some current flow over here, but we know that the input resistance of your IC741 is very high. Okay, see, it is in the order of 2 mega ohms. We have seen 2 into 10 power 6 ohms, which is very high. So we assume that there is no current flowing this way. Okay, so that is why the potential division still holds over here. Okay, so if you calculate Vn over here, Vn will be equal to V naught into R by K minus 1 into R plus R. Okay, so this is nothing but equal to V naught by K, and we know that because of the virtue of negative feedback, Vp equals to Vn. Vp here is equal to Vi. Vn is equal to V naught by K. Okay, so that is how we have Vi or V naught is equal to K times Vi. Okay, so this type of setup, when you use IC741 in this type of setup, okay, so it is called a non-inverting amplifier. Okay, so this is called a non-inverting amplifier. Okay, so let us try to get a more generic formula. Okay, right? Okay, suppose this is Vi. Okay, say this is plus minus. Okay, suppose this is my Vn. Okay, so this is my V naught. Okay, suppose let this be Rf and let this be R1. So what is this value? Okay, V naught into R1 by Rf plus R1. Okay, simple potential divider formula that I have used. Okay, so this potential, this node will be at V naught times R1 by total resistance, that is RF by R1. And we know that this is in negative feedback, and in negative feedback we know that Vp, what is the virtue of negative feedback? Vp is equal to Vn, that is Vi is equal to V naught into R1, sorry, V naught into R1 by RF plus R1, that is nothing but V naught is equal to Vi into, okay, R1 plus RF by R1, that is nothing but V naught is equal to Vi into 1 plus RF by R1. Okay, so what is the gain of the non-inverting amplifier? We have seen that this is a non-inverting amplifier. Okay, and what is the gain of the non-inverting amplifier? So the gain of non-inverting amplifier is 1 plus RF by R1. Suppose you want V0 to be 2 times Vi. Okay, so you choose RF is equal to R1, and the gain is nothing but 1 plus RF by R1, so it becomes 2. Okay, so this is how you design negative feedback amplifiers using IC741. Okay, so uh, the intuition part that I gave you, okay, the integration and the speedometer part is just for understanding purpose. But what is the one main takeaway from negative feedback is, what does the negative feedback achieve is it nullifies the error. It nullifies the error. So that is why when somebody is giving you negative feedback, okay, you can always use it to nullify any errors that you might have. Okay, so that is why feedback is very important. Okay, right. Thank you. If you have any doubts, please ping me.